Welcome to your first semester of mathematical physics. Today, we are diving into one of the most powerful tools in all of science, first-order differential equations. If you have ever wondered how physicists predict the future, whether it is the cooling of a star, the decay of a radioactive element, or the flow of current in a circuit, this is where it all begins. We are going to build your understanding from the ground up, starting with a simple, intuitive idea and working our way through the exact mathematical techniques you will need. Let us get started. Before we look at any math, let us start with an intuitive idea. Imagine you are driving a car, but your dashboard only shows the speedometer, not the odometer. You know exactly how fast your position is changing at any given moment, but you do not know your actual total distance traveled. If you want to figure out where you are at any specific time, you have to work backward from the speed you are observing. This is exactly what a differential equation is in mathematics. It is a mathematical puzzle where you are given the rate of change of a quantity, and your goal is to find the original quantity itself. In physics, we almost always know the rules for how things change, so solving these equations is the ultimate tool for predicting the future state of any physical system. Now that we have a feel for the concept, let us define it formally. A first-order differential equation is a mathematical equation that relates an unknown function to its first derivative. The term first order means that the highest derivative present in the equation is the first derivative. We're only dealing with simple rates of change, not accelerations or higher order variations. Furthermore, the phrase degree 1 means that this first derivative is not squared, cubed, or raised to any other power. In standard mathematical language, we are looking for an unknown function when we are given an equation involving an independent variable, a dependent variable, and its derivative. Solving the equation means finding the explicit formula that makes the original equation perfectly true. This formal definition leads us directly to the general mathematical formula. Here we see dy by dx equals f of x comma y. Conceptually, this equation is just stating that the rate of change of our system depends on its current state and time. Let us break down the symbols. The term dy by dx represents the instantaneous rate of change of the unknown function. The variable y is the dependent variable, which is the actual function we are trying to discover. The variable x is the independent variable, which usually represents time or position in physics problems. Finally, the function f of x comma y represents the known rule that dictates how the rate of change behaves. If the value of f of x comma y increases, it means the physical quantity y is growing at a much faster rate at that specific moment. With the general formula in mind, you might ask why we spend so much time studying these equations. The answer is that the fundamental laws of nature are written in the language of differential equations. Newton's law of cooling, the radioactive decay of unstable isotopes, the discharging of a capacitor in an electrical circuit, and even the growth of biological populations are all governed by first-order differential equations. If we did not have the mathematical tools to solve these equations, we would only know how a system behaves at a single frozen instant in time. We would never be able to predict its long-term behavior or history. By solving these equations, engineers can determine exactly how long it will take for a nuclear reactor to cool down safely. To see how this works in practice, let us look at a fundamental physics problem: radioactive decay.
Conceptually, this formula comes from the observation that the number of unstable atoms decays at a rate directly proportional to the number of atoms currently present. In this equation, N represents the number of radioactive atoms, and T represents time. The symbol lambda is the decay constant, which is a positive number specific to the material. The negative sign is absolutely crucial here because it indicates that the number of atoms is decreasing over time. Physically, if the decay constant lambda is larger, the material decays much faster. If the number of atoms n is large, the rate of change is also very large, meaning many atoms are decaying at that moment.
Now that we have our formula, let us solve it to find the number of atoms at any future time. We are given the rate of decay, and we need to find the function n of t. We use a method called separation of variables. First, we algebraically move all terms involving n to the left side and all terms involving time t to the right side. Next, we apply the integral sign to both sides. Integrating 1 over n with respect to n yields the natural logarithm of n. Integrating the constant negative lambda with respect to t yields negative lambda t plus a constant of integration c. Finally, to isolate n, we take the exponential of both sides. The final answer shows that the number of atoms decreases exponentially over time, meaning the material decays very quickly at first and then more slowly as fewer atoms remain. While separation of variables worked beautifully for radioactive decay, it brings us to a challenge. What if the variables cannot be easily separated? Many differential equations are mixed up in a way that makes them difficult to solve directly. For these, we often rearrange them into a standard linear form. A linear first-order differential equation is one where the unknown function and its derivative appear in a simple, unmultiplied way. To solve this standard form, mathematicians invented a brilliant trick called the integrating factor. This is a special mathematical multiplier that we apply to the entire equation. When we multiply a messy equation by this magic factor, the left side perfectly collapses into the derivative of a single product, making it incredibly easy to integrate. Let us look at the mathematical machinery behind this trick. The standard form is dy by dx plus p of x times y equals q of x. The formula for the integrating factor, denoted by I of x, is e raised to the integral of p of x dx. Conceptually, this factor is designed specifically to force the left side of our differential equation to become a perfect derivative. Let us define the terms. P of x is a known function that multiplies our unknown function y. If p of x becomes very large, it usually indicates a strong damping effect in the physical system. Q of x is another known function on the right side, often representing an external force or input into the system. The symbol E is Euler's number. By calculating and multiplying by I of x, we unlock the ability to solve complex driven systems. Now let us apply this integrating factor to a concrete physics problem. We are given an electrical circuit where the current Y changes over time x according to the equation dy by dx plus 3y equals e to the 2x. We need to find the formula for the current. Because the variables cannot be separated, we use the integrating factor. First, we identify p of x as 3, which gives us an integrating factor of e to the 3x. We multiply every single term in our original equation by this factor. On the right side, the exponents add up to 5x. On the left side, the expression magically collapses into the derivative of y times e to the 3x. We then integrate both sides, which removes the derivative operator.
Finally, dividing by e to the 3x gives our final answer. Physically, this shows a steady-state response driven by voltage, plus a transient initial surge that quickly dies out.
Having successfully used the integrating factor, you might be wondering why that magical collapse on the left side actually works. Let us prove it by looking closely at the algebra we just performed. In our circuit example, we ended up with the expression e to the 3x times dy by dx plus 3e to the 3x times y. To understand why this collapses into a single derivative, we must recall the standard product rule for derivatives from calculus. The derivative of a product, u times v, is u times the derivative of v plus v times the derivative of u. In our specific case, we can set u equal to our unknown function y and v equal to our integrating factor, e to the 3x. This setup is the key to unlocking the magic of the integrating factor method. Let us continue our proof and apply this product rule directly. When we take the derivative of y times e to the 3x, the product rule expands this into y times the derivative of e to the 3x plus e to the 3x times the derivative of y. We know from basic calculus that the derivative of e to the 3x is simply 3 times e to the 3x. Substituting this back into our expanded equation, we get y times 3e to the 3x plus e to the 3x times dy by dx. If we just rearrange the order of these terms, it perfectly matches the messy left side of our differential equation after we multiplied by the integrating factor. This proves that the integrating factor is not magic at all. It is a carefully constructed mathematical tool designed to perfectly reverse engineer the product rule. Now that we have proven the math, let us look at what these differential equations actually look like visually. What you are seeing here is called a slope field. The horizontal axis represents our independent variable, like time or position, and the vertical axis represents our unknown function, y. Every single tiny arrow on this grid represents the instantaneous rate of change, dy by dx, at that specific point in space and time. When we solve a differential equation, we are essentially finding a smooth path that perfectly follows these arrows. The solid colored lines you see, the red, blue, and green curves, are different solution curves. They represent the exact same physical system, just starting from different initial conditions. The slope field dictates the rules of the universe, and the solution curve shows how a specific object actually behaves over time. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that first-order differential equations are the mathematical engines that allow us to predict the future by understanding present rates of change. We learned that for simple proportional relationships, like radioactive decay, we can use separation of variables to isolate and integrate our terms. For more complex, driven linear systems, like electrical circuits, we use the integrating factor to collapse the equation using the product rule. You have now seen the concepts, used the formulas, and proven why they work. Mastering these techniques is your first major step in mathematical physics, giving you the power to bridge the gap between knowing the rules of the universe and actually predicting how the universe will behave.